This may be the world's largest gravitational torsion balance, and it is currently sitting in my backyard. This video is the story of why I built the balance, what I was looking for, and what I actually found. But fair warning, I'm not a physicist, engineer, or mathematician, and I'm not particularly good at math. But I do love to build, learn, and create, and I have built torsion balances in the past. This project has been completely self-funded, and I'm not associated with any universities or labs. It's my hope that people more knowledgeable than myself watching this video will be able to tell me how I may be misinterpreting the results, problems with the testing, or what might be interesting in the results that needs further research. I'll do my best to respond to any questions in the comments section, and if anyone is interested in the raw data or wants to contact me personally, feel free to use the email that's listed in the video information. With all that out of the way, enjoy this story of science and curiosity. Before we get into the actual experiments, what exactly is a gravitational torsion balance? A torsion balance typically consists of two masses suspended at opposite ends of a beam that is suspended by a thin wire. When other masses are brought in the proximity of the suspended masses, a small gravitational force is exerted and the torsion balance twists slightly. The amount of twist of the balance is typically measured by reflecting a laser off of a mirror that is attached to the center of the beam, which is then read on a measuring grid. The earliest known use of a torsion balance to test gravity was conducted by Henry Cavendish in the late 1700s. He actually inherited the device from a geologist named John Mitchell, who died before he could put it to use. With his experimental setup, he suspended two 1.6-pound lead balls from the beam. The beam was enclosed in a case to prevent airflow from interfering with the results. The masses attached to the beam are often referred to as test masses. Cavendish also suspended two 348-pound lead balls designed to be rotated to the case to provide the gravitational force to cause the test masses to deflect. These masses, which are typically much larger than the test masses, are generally referred to as source masses. Cavendish did not have a laser to help measure the deflection of the balance, so he had to visually monitor a vernier scale. Modern gravitational torsion balances typically use much smaller source and test masses, and they can take on a variety of different shapes and forms. Care needs to be taken with any torsion balance test to eliminate non-gravitational forces on the balance. Balances are usually mounted inside of a conductive case and grounded to eliminate static electric forces and to prevent airflow from affecting the movement of the balance. The experimenter must also minimize vibrations, shifting local masses, or local magnetic fields which might affect the results. The smaller the balance is, the more prone it is to these non-gravitational outside forces, which is why I wanted to build a large torsion balance. I want to briefly describe the ideal experiment that I was looking to replicate with this torsion balance project. Take any two equal spherical masses and place them in empty space away from any gravitational influence, including the experimenter. Let's call these mass A and mass B. Next, we'll place a massless measuring grid so we can determine the separation between mass A and mass B. All three objects are stationary relative to one another before the start of the experiment. Mass A and mass B are released from their hold and allowed to gravitate towards one another. The question is, what do mass A and mass B do in this experiment? Additionally, what if mass B were pushed at the start of the test towards mass A? What would that interaction look like? Clearly, the experiment as described is impossible. The reason I bring up this thought experiment is because it would answer my hypothesis. The hypothesis is that there is a mass-dependent distance between gravitational objects at which the inverse square law of gravitation may break down, where gravitation between the objects may go to zero or even become repulsive in nature. The purpose of the design of the torsion balance experiment I'm about to describe is an attempt to recreate and approximate this idealized experiment. Note that the purpose of this experiment was not to look for or test gravitational waves or entanglement. This is the basic concept of the torsion balance that I was going to build. There would be a single source mass that would be moved slowly toward or away from one arm of the balance. I wanted the source and test masses to be adjustable, meaning that I could swap them out with larger or smaller masses as needed. The main question that I wanted to answer with this setup is, when I move the source mass towards the test mass, slowly over time, will I get a graph that looks like this, following the inverse square law of gravitation, or will it look like this, or some variation of this? There are some key limitations in using the experimental design just described to attempt to replicate the ideal experiment. First, the source mass will be attached to a linear actuator, which will prevent it from moving in response to any forces that may be acting upon it, whereas in the idealized experiment, both masses can move from any pressures and forces between them. Second, the test mass is tethered. It can move in response to small forces acting on it, but it will spring back and it cannot move away indefinitely, if there are any repulsive forces present. Here is a visualization of what the difference in results might be between the ideal experiment and the torsion balance experiment if there were a repulsive effect that developed at distance r, separation, of mass A and B, as mass A approaches mass B slowly. Note that in the ideal experiment, mass A and B can exchange energy, and A slows relative to B, and B moves away from A and continues. In the torsion balance test, this cannot occur. While this is all hypothetical, it is important to keep this concept in mind when analyzing the test results. Before we get into the details of the experimental design, I want to briefly discuss the start of the project. I built and tested all of this in my dining room because I don't have a garage, basement, or extra rooms in my house. This proved to be incredibly inconvenient for several months. When I would run the test, I would do it in the middle of the night when everyone in the house was asleep. I would section off half the house to keep my very curious cat from interfering with the balance while I was recording. I had to engineer cat retaining walls that she would defeat and I would have to redesign. It was a constant battle. It annoyed my wife and daughter that they would have to avoid the half of the house with a kitchen at night. I would have to wake up at various times of the night to stop the motor so it wouldn't slowly crash into the balance case. I was always concerned that refrigerator motors or HVAC system were causing vibrations that might mess up the results. Everyone was happy when I moved the balance to the backyard. The large box on the right houses the balance and the source mass movement rig. The smaller box on the left contains the measuring grid, recording equipment, and the movement counter. The tube in the middle is the pathway for the laser that's reflecting off the balance. I should point out that the walls of the shed are not connected to the floor inside. They rest directly on the ground. This is to prevent wind and precipitation from vibrating the floor and the balance. This is a viewport for visually monitoring the experiment. Later on, I added this viewport on the side so that I could see how close the source mass was to the case. This is the grounding rod for the balance. Here I'm removing the access panel. Let's start with the balance itself. The case is constructed with aluminum, brass, and special conductive tape. This is the viewport in the top of the balance. This is for monitoring the position of the test masses during calibration. This is the window on the front of the case so that the laser can reflect off the mirror on the balance. This is the balance support frame. It stands about 7 feet tall and is made of wood, aluminum, and brass. There's padding underneath the base to reduce vibrations. Inside the case is the balance, test masses, and suspension wire. The suspension wire is made of beryllium copper, is approximately 167 centimeters long, and has aluminum ferrules crimped on each end. These are the different wire thicknesses used during testing. The suspension wire is attached to the balance by being compressed between aluminum plates with a space for the ferrule, as shown in this picture. The brass nuts and bolts holding the aluminum plates together were only hand tightened to avoid damaging the wire. The other end of the wire is compressed between two L brackets, which rest at the top of the balance case. These can be spun and turned to adjust the position of the test masses within the balance case. Once the balance is suspended and adjusted, a grounding wire is attached to the top mounting brackets and a cover is placed over it. The lead spheres attached to each side of the 4-foot aluminum beam with a brass loop that is embedded in the lead and a brass bolt. The case is also connected to a copper grounding wire. For the experiments conducted so far, 3 different masses have been used as the test and source masses in different combinations. I built the balance on the fly without much consideration of how I would mount the test masses and cover it with the case. I won't go into the details of the mounting process, but I can tell you that it's fairly stressful mounting 100 pounds of lead from a 1mm wire. I have to use 2 scissor jacks and a lot of patience, but I've broken more than a couple wires over the past couple years. I tried finding an off-the-shelf linear actuator to push the source mass at very slow speeds, but I could not find one that could move as slow as I needed, so I decided to build a custom actuator. This is a 12-volt, 5 RPM worm gear motor attached to a 2-foot stainless steel threaded rod. Notice the magnet attached to the coupling. As the motor spins, it triggers a counter that is mounted in the recording box. This can be used to measure the linear motion of the source mass. Connected to the motor is a voltage controller to control the speed of the motor and a switch that can control the direction of motion and stop the motor. Both of these can be operated with remote controls, so I don't have to go in or near the shed while the experiments are being conducted. As the threaded rod spins, it pushes an aluminum rod into an aluminum suspension arm. The source mass is attached to the bottom of this arm, and there is a roller system at the top. The roller is housed within a stainless steel track. This whole rig is supported by a wood and aluminum frame, and the whole frame is lifted off the floor about 1 centimeter and attached to the ceiling and the walls. Remember that the walls are not connected to the floor. This is to prevent the floor from tilting as the mass moves forward on its track, and also to reduce vibrations that may occur from the motor. Note that there is a tarp air block underneath the floors that attaches to the bottom inside of the walls of the shed. This is to prevent airflows, moisture, and bugs from getting into the test area. I've tried a few different lasers during testing, and I found that the best, most reliable laser was a standard construction self-leveling laser. I wired the level so it could run continuously off of power from my home. The laser is reflected off of the mirror and into the recording box. Inside the recording box we have a camera to record laser movements. This was just an old cell phone that I had. A measuring grid. This can be any old ruler that has millimeters. An adjustable light. Because the box is sealed and dark inside, without light you can't read the ruler, and too much light and it washes out the laser light so you can't read it very well. So an optimal amount of light is needed. The counter. This counts the number of motor rotations and lets you know how far the source mass has moved, where it is, if it's about to hit the case, and it is used when recording data for position of the source mass. The remote camera. This is important for monitoring the progress of the experiment. It lets you know if the camera is still working properly, that the laser is still visible on the measuring grid, and most importantly, when to stop and start the motor remotely based on the number on the counter. Before any testing, I would zero the source mass by pushing it all the way to the case. When I move it away, I know exactly the number of rotations it takes before I hit the case. Hitting the case with the source mass during testing would likely throw off the results, and this was avoided at all costs. For each test performed, the laser movements are recorded, and the recording is transferred to a computer and opened in video editing software. Zoom and timescales are optimized, and the stop points of the laser oscillations are recorded using a frame-by-frame analysis. It's time-consuming, but it works well. For each data point recorded, the oscillation number, laser position on the grid to the nearest 1/4 millimeter, the time, and the motor rotation number are all recorded in a spreadsheet. Other relevant experimental data are also recorded, including date, time, and the type of test being performed. There are several ways of evaluating the results, but the most useful is graphing the average of the successive data points. This gives a moving average or equilibrium point of the balance. I'll also sometimes take the average of successive equilibrium points, which is essentially taking an average of an average. I don't know if this is good to do, but it seems to smooth out the graphs. Here's an example of using the average of the average to smooth out a graph. This usually is not necessary for most tests. Note that decreasing equilibrium point values indicate movement of the test mass toward the source mass, while the opposite indicates movement away. In my early testing, I only recorded the data while the motor was running. I later learned that the data after the motor stopped is just as interesting. I would like to make a special note that some of the most important points on the graph to make note of are the points that occur in multiples of the motor runtime. For example, if the motor runtime were 1 hour, you would want to mark the graph at the 2 hour, 3 hour, 4 hour, and 5 hour mark. Also, the first red data point represents the motor start point, and the second red point is the motor stop point. Yellow and white data points represent points of interest. The motor time points are denoted in the graphs by the unfilled data points, like these. Another way I like to evaluate the results is by independently graphing the towards and away swings in the same graph. By doing this, you can visualize how far the test mass is swinging in total and how this changes over time. I should note that the purpose of the testing is not to quantify any forces, but to view the direction of the movement of the test mass relative to that of the source mass. Once the data has been recorded and graphed from multiple tests, comparisons can be made between them. Before we go into the interesting results, we have to go over some of the things that I learned during initial testing. First, I learned that the balance moves on its own at all times on a 24-hour cycle. It took me about 6 months to figure out that this was occurring, so I decided to do several successive 24-hour tests without having a source mass present. Here is an example of a control test without a source mass. Here is the same test graphing each swing. Here are the results of 3 12-hour tests, all starting at 6 p.m. and ending at 6 a.m. But what is causing this 24-hour wave pattern? My best guess is a weak shift in the magnetic field at the surface of Earth, resulting from the interaction from the Sun and Earth. In reviewing the literature, I found references to other researchers operating torsion balances that have experienced similar issues. Also, here is a graph of the 24-hour geomagnetic field recorded by the National Geomagnetic Service in Edinburgh, It matches the graph that I recorded. It should be noted that the source and test masses used for these experiments are made of lead, which is diamagnetic, but they are certainly not 100% pure lead and likely have some trace amounts of iron and other metals. I have also noted significant activity in the balance when auroras have been visible here in Massachusetts. So how does this diurnal shift in the balance affect the test results? This certainly impacts the slowest tests the most. In some of the longer tests, it takes about 15 hours for the source mass to move to the case. This doesn't affect the faster test as much, but it needs to be considered when analyzing the results. It makes me wonder if I had a control balance right next to this one, whether I could use the readings from that to eliminate this geomagnetic effect from the data. I can tell you with certainty I am not building another one of these. We'll save that for the small scale tests. What I typically do when analyzing my results is just compare the times of the test to the same times in the 24-hour control data. I try to update the 24-hour control data occasionally, as I suspect that it shifts over the course of a year. Second, I should note that I tested the balance to see if it shifted or changed based on temperature or temperature changes. If there were temperature-related changes, I couldn't find them. And finally, I have done readings of the balance during storms with 60-mile-an-hour winds and rain, and I have found that there is negligible deflection and shifts in the balance during these situations. This was actually quite unexpected considering how sensitive the balance is. Here are the diameters of the test and source masses in centimeters and rotations. This will become relevant later. Here are some control tests to demonstrate how sensitive the balance is. The results inform us as to how much deflection of the balance we should expect with different test and source mass combinations. In this test, the source mass is removed from its position at the case, then replaced after a period of time. Here's the graph we get. Note the average deflection is about 0.5 centimeters. Here's another control test, but with a smaller test mass. The source mass is removed. Note the 0.6 centimeter deflection. This is a repeat of the previous test. Here are the large source masses placed. Note the approximately 0.4 centimeter deflection. Here, a 25-pound source mass is used. Using the control test results, we now know how much deflection to expect when placing and removing the source masses. Note that for these control tests, we're placing the source mass on the side of the balance opposite the mobile rig, so deflections will be in the opposite directions for gravitational traction when compared to the usual tests we've performed. It should be noted that the test mass is typically located closer to the inside of the case on the mobile rig side versus the opposite side. So if we repeated these control tests on the mobile rig side, I would expect the deflections to be slightly larger. The reason the control tests weren't done on the mobile rig side is because the mobile rig itself got in the way. In this section, results of tests with the source mass moving toward the test mass are presented. The following is the results of 6 identical tests with this setup. Note that the percent next to the speed is the motor power setting for the test. The time listed is the time from motor start to motor stop. The distance is the distance the source mass is moved in centimeters. The source mass is stopped at the case. Note the similarities and differences between each of the test results. In test 50, 52, 59, and 61, the test mass deflects toward the source mass as it approaches, as expected, but not in test 55 or 57. Deflection in test 61 is less than expected based on control tests. Test 57's overall shift is in the opposite direction we would expect. Test 50, 57, 61, and possibly test 55 have significant arcs within their data that are 5 data points long. Is there a significance of the 5 data points? The oscillation number on the x-axis represents time. In this test, successive oscillation numbers equals 1/2 the oscillatory period, or 3 minutes and 40 seconds. 5 data points represents about 14 minutes and 40 seconds, but it also represents the movement of the source mass in that period of time, which is approximately 58 rotations, or 8 centimeters. This is approximately 1/2 the diameter of the source and test masses for this experiment. This may seem irrelevant, but after having analyzed multiple tests with multiple test and source masses, it appears there may be some correlation between the diameters of the source and test masses and wave patterns present within the results. I'll explore this in more detail in a future video. Tests 50 and 61 have what appear to be a repeating or symmetric wave pattern. From here forward, individual test results will be presented. Note the large shift on motor start in this test. This level of shift is not expected as the source mass starts moving over 32 centimeters from the test mass. Is this large initial shift incidental noise or something else? Also note the away shift here. Also note symmetry of the graph about motor time 1. Note the W shape about motor time 1 and 2. These W's are regular signals in the data of many tests. Also note these two smoother and straighter sections of data. Both are 8 data points long. Here are the swings graphed separately. Here's test 57 from earlier, the one that deflects in the opposite direction as expected. Note the symmetric dip around the motor stop. Note that this J-shaped wave and the mirror image J wave are symmetric about the motor stop points. Do these represent a reversed wave that occur on motor stop? Note that this J curve is also 12 data points, with motor time 2 having a similar dip as motor stop. 12 data points correlates with 164 rotations, or about 1.5 diameters of the test and source mass. Here is the first motor time point. Note that these two arcs are identical. Both are 22 data points, or equivalent to the time it took the source mass to move 1 diameter. Note that on close approach, the test mass moves away and not toward the source mass. The red line represents an approximate expected deflection of the test mass when the source mass is at the case based on the control test results. Note the lowest part of the large dip intersects with the expected deflection. Note this small bump here. Note this sinusoidal arc and its midpoint. Half of this arc is equal to the time between motor start and start of arc at white 1 point. Next, we will compare a similar test but with a larger test mass. Note this bump. This dip represents the time it took the source mass to move approximately 15.5 centimeters, or about 1 diameter of the source mass. Note that, like the previous test, the test mass moves away on close approach. This line represents the predicted deflection point based on controls, approximately 0.6 centimeters. Note that the low point of the large dip intersects with the expected deflection. Why would this occur? Why does the test mass move away on close approach? Interestingly, but probably irrelevant, if we cut off everything after the lowest point of the dip, this is the same graph predicted in the hypothesis and by control tests. But how could gravity cause a maximal deflection of the test mass 9.4 centimeters from the case? The time from yellow points to motor stop are equal, and the time from the motor start to the first yellow and the second yellow to the motor time 1 are equal. It should be noted that the two yellow points have an identical equilibrium point. Here are tests 19 and 41 side by side. Note that there is essentially no change in the equilibrium point from motor start to motor stop. The red line is an approximate expected deflection point. Note the large shift on motor start. Rapid transition from test mass equilibrium point moving away to toward right here. Note these three peaks are equidistant from one another, and the last one is also motor time 3. Note the lengths of each side of the peaks are equal. White lines represent 2 data points and yellow lines 4 data points. The results of test 39 are what I expected most test results to look like, but this result was an outlier. Note the sharp transition at oscillation 25. The overall deflection from start to stop is in the expected range. Note the sudden shift of direction at oscillation 10. Also note the spike at motor time 1. In this test, the overall movement from start to stop is away. Here is another test that has a jagged arc. In this very slow test, the stop point has the lowest equilibrium point. Here are the swings graphed separately. Notice the swings widen significantly in the middle part of the graph. When we compare this test result to a 24-hour control test, they look very similar. Did I just happen to start and end the motor at just the right time to have the stop point be the lowest equilibrium point? Note the difference in the magnitude of the equilibrium points between test 1C and the 24-hour control. This is a repeat of the previous test with an earlier start time. Notice the similarities. This is a graph of the swings separated. Here is a side-by-side of test 1B and a 24-hour control test. Here is a side-by-side of test 1C and 1B. Here is a series of 6 results from identical away tests. These results are of the movement portion of the test only. The source masses are started at the case and moved away at 0.54 centimeters per minute. Notice the variation of the results. Remember that shifts in this direction mean the equilibrium point of the test mass is moving away from the source mass and toward the source mass in this direction. In 3 out of the 6 tests, the test mass moves away overall between the start and stop point. 2 have no significant shift. One has a slight toward shift. We expect an away shift very early in the tests. We observe an away shift within the first 4 data points in 4 of the 6 tests. In 2 of the 6 tests, an away shift is not observed early in the test. In these 2 tests, initial results are jagged. Let's look at some away tests in more detail. Note that the away shift from start to stop is in the expected range based on control tests. Note the symmetry of these 2 arcs. These are equidistant from the motor stop point. Each side of both arcs are 4 data points long. Arcs are in opposite directions, and second arc ends on the first motor time point. Notice the large shift at motor time 2 point. These dips are close to the time it took the source mass to move 1 diameter. This W is approximately equivalent to the number of data points of the previous 2 other large arcs. The red line is the approximate predicted deflection. This test has some similarities to the previous test. This dip is similar and is about 1 diameter the source and test mass. This test also has a W wave that has an equal number of data points and that is approximately 1 diameter. This arc is also approximately 1 diameter. Here is the swing separated graph for this test. For this test, the test mass moves less than expected between the motor start and motor stop. Note the dramatic shift in the graph after the motor stops, and note that the shift stops abruptly at motor time 1. Note motor time 2 and motor time 3 are at peak points. Note that the away shift between motor time 1, motor time 2, and motor time 3 are almost equal in amplitude. This will be observed in other tests to be presented. This test, like the previous one, has smooth, subtle arcs through the source mass movement data points, and it shifts away from start to stop, but not as much as expected. In this test, the data is fairly flat, but with significant jumps at or near the motor time points. Interestingly, the balance does not shift at motor time 2, but the amplitude of the shift at motor time 3 is about twice that of the shift at motor time 1. Here is the expected shift from start to stop based on control tests. It appears to be shifting in a stepwise fashion correlating with the motor runtime. Here is the swings separated graph for this test. Notice how only the away swings shift at motor time points until motor time 4, where the toward and away swings shift. I believe this may be an important clue that may help clarify the interactions between the source and test masses. The resolution on this slide isn't great, but is a clear demonstration of the W signals. Here is the expected deflection. Note that these two flat sections are both 10 data points long, as is this one. Note that these two have equal amplitudes. As in the previous test, it appears it takes about 4 motor times for the test mass to deflect to its predicted position. The expected away deflection occurs in this test, but note the abrupt shift here. Note these W signals. These 5 to 6 point W's do correlate with one diameter of the source mass. It appears the W signals migrate to the left between successive motor times, as in the previous test. Note the shift of the W signal relative to the motor stop and motor time points. Could this be a sign of a complex wave? The test mass deflects away in an amount expected in this test. Note these two white transition points. They are exactly 1 motor time apart. If you count back 1 motor time, or the equivalent 11 data points, from here, it leads you to this point. And if you count back 1 motor time further, it lands you at the motor stop point. Like the migratory behavior of the previous 2 tests, if you count the number of data points between the white points and the next motor time, it gradually increases. This will be the final test that I present in this video. Note that this test is a little bit different than the others. This test is only run for about 80 rotations, which is about 11.1 centimeters in total, and is run at 100% power. I also placed a large stationary source mass at the case on the side opposite the mobile rig. Note the significant toward shift that occurs just after the second motor time. Note the W signals. Note that the time from the motor start to the first yellow peak and the first yellow peak to the second yellow peak are equal. Also note the similar migration of the W waves as in the previous tests. So here are some conclusions from the results. Movements of the test mass vary widely between identical tests while the source mass is moving. There appear to be significant shifts of the test mass equilibrium point at or near times that are multiples of the motor runtime. There appears to be a 24-hour cycle to the movement of the balance, possibly due to magnetic fields. With regards to the original hypothesis, for toward tests, there may be areas where repulsion is occurring, but these occur in waves and the positions of these shifts vary between tests. There are signals within the data suggesting reversing and reflected waves. There may be signs in the data that the test mass is moving in response to a complex wave that is a combination of a wave from the source mass and a wave from the test mass. The wavelength of these waves appear to possibly correlate with the diameter of the masses. I'll explore this further in a future video. The movements of the test mass when the motor is stopped during away tests are more than I would expect at those distances and may show signs of wave reversals. Are these results signs of entanglement? Does entanglement occur at all scales? The data presented in this video is meant to highlight some key features of the results, but not to be a detailed analysis. Since this is outside my area of expertise, I'm not sure the best way to analyze the results. Perhaps somebody watching this video who has signal analysis experience can give me some pointers, particularly with regards to the possibility of a complex wave reflecting between the two masses. I've decided to put the data from a portion of my test on Patreon, which anyone interested can download for a donation of their choosing. The Patreon link is in the video description. You can email me at the email address listed here, and feel free to leave comments.